when you talk about, there are multiple engineering materials. One can be, so primarily most of the engineering metals which we use are metals. And I'll explain what metals are. Then we use something called ceramics. Then we use polymers. Then we use glasses. Then we use, nowadays we are using something called hybrid materials, which have properties of two of these materials, and they are called hybrids. And a good example for that is composites. So I'll talk a little bit about composites in detail, because metals, ceramics, polymers, you know them. On the other hand, composite is something new. So I'll talk in some detail about composite, give you some ideas about how do you determine the composite properties from its constituent materials. And then we'll show you a nice video of the Dreamliner, how the composites are manufactured and how do you make a system. So a case study of Dreamliner is what we will cover. So that's what the plan today is. Then each of these material properties, each of these materials will have certain properties. Now, these can be mechanical properties. So the mechanical properties which I'm talking about can be modulus of elasticity, then yield stress, ultimate stresses, density, Poisson's ratio, and then a few other mechanical properties can be, what would that be other than this, G. So these are some of the mechanical properties which you would come across. Then there are thermal properties. Thermal properties will be thermal conductivity. Rho is also a mechanical property as well as thermal property, because it affects the diffusivity. Then thermal conductivity, C, specific heat, C, thermal conductivity, density, specific heat. Then you can talk about coefficient of thermal expansion, alpha. And you can also talk about latent heat of fusion, latent heat of melting. These can be some of the thermal properties. This is not a comprehensive list of thermal properties, but these are some of the thermal properties which you would see. And then there can be emissivity. These can be thermal properties. Now, electrical properties can be electrical conductivity. And then very similar to that, electrical resistivity. Electrical conductivity, looks like it is acting up, just give me a minute. Electrical conductivity, and electrical resistivity. Then there will be optical properties. Optical properties can be refractive index. What else? Then it can be reflectivity, transmittivity, and then reflectivity can be there, transmittivity can be there, absorptivity of the material. Right. So these can be optical properties. And of late, what is important is also, if you think about it, one of the most important things these days is eco properties. So if you don't know what is ecological properties, it can be biodegradability. So you have to be able to degrade the material, because you cannot use something that is environmentally not very friendly. So you have to choose materials which are biodegradable. Right. So biodegradability is also one of the material properties these days. So if you look at the history, the evolution of materials took place. The first material, you'll be surprised, which was found by human beings, the first metal was gold. Gold was the first material which human beings found, because gold is a noble material and it exists in nature in non-alloyed form. Every other metal, the human beings had to process it, except gold. Gold was in its native form, in all its glory. So man discovered gold around few thousand BC, and they're still using gold. So gold is something that has been with man for a long, long time, right? Then they also used some sort of, I would say, composites and polymers. They used wood. Wood is a classic example of a composite. Although it is a natural composite, but they used wood. They used skins and hides of animals. They used natural fiber. They used cotton and other naturally existing fibers. They used so the Egyptians actually used a composite. A composite basically means is that it's a combination of two materials. So it's a chemically distinct. So both these constituents are chemically distinct. They are not in alloyed form. They are not intermixed with each other, but they maintain their chemical distinctnness even while they are in the composite form. So there is something called adobe bricks, which they made by using fibers and the mud. So they put straws, or for the lack of better word, I don't know if you know, when you harvest your wheat, you will get that pual. That pual, what they used to use, that straw which is there, the straw is used for thatched roof and whatnot. A lot of villagers use that leftovers. These days people are using harvesters, so we don't get that pual anymore because we are not doing hand harvesting. So that pual now it comes in powder form, and people are burning the straw which is left in the fields, and that is getting a lot of pollution. But earlier what people used to do is people used to cut it by sickle and get long strands of straws. And the prehistoric human being, they mix this with the mud. Not only prehistoric, I think they were doing it even few decades back for making mud houses and whatnot. So you mix that with mud and make bricks out of it. And the Egyptians used to call it adobe bricks. That's a classic case of composite where you get, because mud would not have any tensile strength. But the moment you add that straw, there will be tensile strength. So this is something which is a classic case of composite, which man figured out how to make composites back in the day, even in prehistoric times. And they were using ceramics, bones, glasses, stone. These are all examples of ceramics and glasses. So all three classes of materials were being used. As people got evolved around 1000 odd BC, man discovered iron. Specifically, some of the Central Asian cultures discovered iron, and it was iron and use of horses which actually gave them an edge over their other competitors. So some of the civilizations which actually depended upon just copper and bronze, the Chalcolithic period, they were actually superseded by the people who had iron. So just to let you know, Indian iron making was very advanced, and the Greeks used to source swords from India. And there was a lot of fame about Indian swords and Indian steel. So in fact, some of the wood steel and crucible steel, which the West discovered only 19th century, Indians were making crucible steels way back in some BC and exporting it to the Greeks. So so this iron gave a lot of these cultures an advantage. And then people started discovering glues. They got some form of cement where they could join their stones and make big buildings out of it. And then as we evolved, we started using other things. We discovered steel in some around 1800s. We discovered long back. We discovered in actually some BC, but industrial steel making started in 1800s. And then it just changed the entire scenario. Okay, so that's what there. And then what they did, they started doing we started discovering super alloys, and now we have composites also. We have some special super alloys, special materials, light materials. So now we have an entire gamut of materials with time. So that's what I want to give you, some of the history of how materials evolved. So right now in our disposal, so we have multiple things at our disposal. We have metals, we have polymers. So metals, and I'll define everything. And then we have ceramics. So metals are the most sought after material. Metals are very ductile, and they are strong, they are ductile. So you can use it for weapons, you can use it for structural materials. So metals have lots and lots of advantages. Ceramics have very high strength, and they have high strength. They have high strength, and high temperature resistance. high temperature resistance. High temperature resistance. So ceramics have applications where there is high temperature and high strength required, but the problem is they have no ductility. So ceramics have no ductility, and glasses don't react with anything. So you can use it for drinking devices and the like, right? So glasses can have very applications where you want to store food and where you want to store chemicals. So glasses can have a lot of applications that way because it doesn't react with chemicals. So the polymers have this, what is it called, very high elongation. But they are easy to form. That's why polymers are very popular, because you can make millions and millions of pieces. So you can make cutleries, millions and millions of it. You can do very. This is so polymers. There are a lot of these applications of polymers, because you can make a in the due course. So elastomers are there, which have very high extension. So you can use for same load, you can get very high extension and deformation. So elastic and all these kind of materials where you want very high elongation, you can use these materials. So, and then of late, what you can do is you can have a hybrid material, which actually possesses the best of the properties of multiple materials, 2 or more in some cases. So those classes are called hybrids, and a composite is a classic example of hybrid. Composite material is a classic example of hybrid, right? So composites are hybrids. Okay. So let me just give you some example of metals. So stiff materials with very high elastic moduli, and they exhibit ductility. They can be made strong by alloying, mechanical and heat treatment. So you can do mechanical and heat treatment. Basically means if you deform it, it becomes stronger. So if you do forging, so any forged part will be much stronger than as cast part. And you can do heat treatment. So if you heat it beyond a certain point, austenite forms, and if you cool it very fast, martensite forms in steels. And there are different mechanisms for hardening of aluminum and copper also. So in a nutshell, you can either do heat treatment or mechanical treatment to make it strong. And these metals have reasonably high elastic moduli. So basically, they are elastic moduli high means they're stiff. So if you apply load, the deflection is minimal because they have stiffness, inherent stiffness, and they can be made strong and they exhibit ductility. So you can actually make it very ductile. So you can draw cables out of it. You can make wires out of it. And so a lot of these things can be done using metals. Then there are ceramics and glasses. The ceramics and glasses have very high moduli. So moduli in some cases can be 20 GPa. What am I saying? 20 GPa can be actually strength in some cases, very high strength. But problem with this is, and the modulus is very, very high. But what happens is, if you see, steel's modulus is about 200 GPa. So steel strength will be maximum 400 MPa, and then some cases it can be till 2 GPa. Very high rocket grade steels can be 2 GPa or 3 GPa. The ceramics can be 20 GPa yield strength, but they will just, you put there and it will break there. So there is no plastic deformation with ceramics, although they're very strong, and their E values can be much higher, much higher than metals. So 200 GPa, they can be probably an order of magnitude higher than metals. Stiffness is very high, tensile strength is very high. But what happens is they actually fail in fracture. So you just pull it, it will hold till, so if you take a stress strain curve, it will go like this, very high slope, but it will just break right here with no plastic deformation. Right. So that is the big problem with ceramics. It has low tolerance for if there is any hole or crack, the crack will just propagate and fail. And it has good application in making some bearings, biomedical implants, where you want low wear. They're extremely hard, so wear will not be there. So you can make tools out of it. You can make bearings out of it. Very high speed bearings are ceramic bearings. If you go even higher than that, then you will have to go to air bearings and even magnetic bearings. If you go very, very high because you don't want any wear, so it has to be suspended. But between your ball bearings, the balls will be made of ceramic. So you can actually make very high speed bearings even in mechanical bearings using these kind of ceramics. The problem is it has large scattering properties. So properties have a lot of variation. The polymers and elastomers are materials with low moduli. The modulus is low, meaning that if I apply load, they will deform. But the strength is still high. So strength basically means your sigma U is still very high, not sigma Y, because they will start to yield very fast, but they will not fail. So ultimate strength can be as good as metals. Elastic deflections can be very large. They exhibit creep. This is a very important thing. If I actually put load on that and do not change the load. So in metals, this creep issue is not very prominent except in high temperature. If there is high temperature, then at a constant load, it will deform. Otherwise, in metals, you have to increase the stress for strain to increase. But in this case, what happens is even at constant load, you will see with time there will be deformation, and it is called creep. It has very high strength to weight ratio. That's very good thing. You can get very high strength, but the weight is very low as compared to metal. So if you want to have same strength in a metal, the metal will weigh much, much more. And you can injection mold it. You can make very, very extremely complex shapes, which is not easy for metals to make. Very thin, very complex shapes. So all these new fascinating things you see, right? All the enclosures of your phone casings, your computer casings, your chairs, your tables, your water bottles, your tiffin things, everything is made out of polymers these days. Okay, so polymer has inherent advantage that it can be made into complex shapes. Now comes a very interesting material. I will dwell on it for a little bit before I go to other things. It's composites. So composites basically means it consists of two chemically distinct phases. So there will be two chemically distinct phases, meaning there will be a primary phase, which is called basically the strengthener. Primary phase is the one in which holds the secondary phase. So primary phase is called typically matrix. Primary phase is called matrix. And the secondary phase is typically called some sort of a fiber or strengthening thing, fiber or filler, whatever that thing is. So this is for primary holds the secondary phase. So it can be either polymer, it can be metal also, it can be ceramic also, because composites can be many kinds. But in most cases, most common composites, you will have a polymer primary phase. That polymer can be either thermoplastic or thermosets. Most of the common ones are thermosets. They are epoxies. They are like resins. If you have seen araldite is a typical thing which will be there in the composite. So if you imagine, you take two different resins, mix it, and put some metal particles in it, you'll get a composite. If you just put some iron filings in araldite, what you get is a composite, right? Or if you put some glass particles in your araldite mixture, you have two things, right? In the resin, you will have a hardener and you will have a resin. So basically, you go ahead, you mix it, put some glass particles in there, and out comes a composite. So actually, that's how composites are made. So when you see most of the composites, you can lay the fiber and put epoxy, which will have a epoxy resin and a hardener. So that's how you lay up layer by layer. So there are two ways to do it. Either you do hand layup, or you can do automated layup. I'll actually show you some of the examples today in how the Boeing plane is made. So you'll get some feel for it. And but there can be metal matrix composite also. There can be ceramic matrix composites also. So all three can be there, but most popular ones are the polymer matrix, or whatever you call composite. In your general parlance, a composite means a polymer matrix composite, or either glass or carbon. The secondary phase is called the embedded phase or the reinforcing agent. So you actually put some either hard phase or some specific material to get an additional property. So primarily it is to strengthen the composite. It can be in form of fibers, particles, flakes, all sorts of things. It can be one of the three basic elements, materials, polymers, metals and ceramics, or carbon or boron. You can also have carbon and boron there. So basically, when you put composite materials, you can put fiber, you can put a flake, you can put a particle, or you can have lamina. So what you do is you can create directional lamina. I'll actually derive a nice thing for you to basically tell you, if you have fibers, what kind of enhancement in property you get. Okay. So there can be fiber composite. These are short fiber composite. Short fiber composites. This is particle composite. This is laminar composite, means so you can have different orientations, say 0 degree, 45 degree, 90 degrees. So your fibers will have certain orientation. It can have 90 degree orientation, it can have 0 degree orientation, it can have 45 degree orientation, 60 degree orientation. So you can engineer the property in different directions. So you can actually have composite where in the loading direction. So I can engineer a composite to have certain desired properties in desired direction. That's the freedom you get using a laminar composite. You can also get a woven composite, which basically means that you have like a sweater. You have seen the woven sweater, right? So you have fibers like woven, like in a case of sweater. And then of late, you are having a three-dimensional composite also. You can do 3D printing of composite also. That's the latest technology which is coming in. So all sorts of composites you can create. But the class of composites can be metal matrix composite, mixture of ceramics and materials, cemented ceramics, called cermets. So basically metal matrix composites, if you see, I don't know if you have seen a cutting tool. Most of the cutting tools which are tungsten carbide is a ceramic-like material. Although it behaves like a metal, it has high thermal conductivity. It also is electrically conductive, but tungsten carbide is actually a ceramic with good properties, with metal-like properties, but it is very hard. So what you do is in tungsten carbide, you mixed cobalt metal with it. So what it does is it imparts toughness. So you can have metal matrix composite. So you can have tungsten like cobalt. So that's also a composite which actually creates certain benefits out of it. In metal matrix composite, what you do is you take aluminum matrix and put silicon carbide there. Now, once I have silicon carbide, I actually get higher strength in the aluminum. So ALSIC composites can be there. So some of the engines which people make, they use aluminum silicon carbide composite. You can have ceramic matrix composite, where you can have aluminum oxide and silicon carbide are the main matrix, and you embed. So basically you can have silicon carbide composite, which is actually latest. So very high temperatures if you want. If you want to, so my efficiency in any engine, if I talk about aerospace engines, it is limited by the material. Right now, most of the hot components of engines are made of nickel superalloys, Inconel. So right now they use something called nickel superalloy. Let me go back. They use something called nickel superalloys or Inconel class of materials. What we do is we use the materials which we use. The material which we use is basically nickel superalloy. Nickel superalloy, which is called Inconel. But if you really want to use this material, a better material would be ceramic matrix composite. I can go very high. So right now my temperature is limited to, I can go with Inconel, I can go up to 1000 degrees centigrade. Little bit, 1000, after 1000, 1200, it starts to soften then. But if I use this ceramic matrix composites, I can go very, very high. I can go up to, say, 2000 degrees centigrades. So I can have a much more efficient engines, right? I can get a lot more power in my turbine engines for fighter planes and whatnot. So these are the future engines will be made of these silicon carbide. Then there is something called polymer matrix composites, where so these are the most common ones these days. People use for making cars, planes. This is the material of choice because there are multiple advantages. If I have composites, I can engineer the properties to be very high, but the strength to stiffness ratio is very good here. strength to stiffness ratio. Oh, sorry, strength to weight ratio. Strength to weight ratio. Strength to weight ratio, and even stiffness to weight ratio. Strength to weight, you get very good. Now, which basically means that the plane which I was making, if you take example of Boeing 777 and Boeing 787, Boeing 787 has 50% composites. Boeing 777 was some 60 to 70% aluminum. So now my plane is much lighter. So my plane is much lighter, meaning it is more fuel efficient. So with the same amount of fuel, I can go much longer, which makes good business sense for me. So composites are the choice of materials for aerospace, wherever weight is critical. For aerospace, for defense, if I want to make a missile casing, I make a very heavy missile casing, means I'll have to have a larger rocket power, right? So if I make a lighter casing, I can go farther. So I'll get a larger strike advantage. So now, in classification of composite materials, if you say a matrix provides the bulk, embedded phase, and shares the load with primary phase. But load primarily comes from your fiber and not the matrix. And reinforcing phase, as I said, it can be of various shapes. You can have one-dimensional, you can have planar. One-dimensional meaning that there is a direction of fiber. Then planar means there is a woven fiber, like this, like how you do your sweater, right? Up and down of the two fiber, like a cloth, woven cloth. And then you have random and three-dimensional fibers. This is what people are trying to move on to three-dimensional. So you can have a printed a three-dimensional composite. So you can have, so right now the way people make composite is, third dimension is just you keep on laying material up. But if you do a three-dimensional polymer, you can actually create polymer in 3 dimensions. That's something which people are exploring now. And type of phases which people use is, if you see, most of the strengthening materials, glass fiber is very popular. It's cheap. So all your roofs, if you see, in some cases near the fluid mechanics lab, the green thing, it's actually a fiberglass composite. Some of the chairs which you use, high strength chairs, some of the pipes, these are made of glass fibers. But glass fibers are cheap. You can have either E glass or S glass, and you see E glass has about modulus is about 500,000 psi, which is if you see higher than steel. S glass, if you see, is around 5 times the tensile strength of steel, and density is only 1/3 of steel. So you see how much advantage you are getting. You're getting a very light material, but super strong material. You can also have even better reinforcing phases, carbon and graphite. So carbon has tensile strength 3 to 5 times than steel. So 5 times the steel, but density is 1/4. So you get very high, very high strength to weight ratio. Boron has very high elastic modulus, but it has very high cost. So this is actually used only in defense. Then ceramics you can use silicon and aluminum, but these ceramic composites are typically used in high temperature components. And metals you can use in polymers. For some applications you actually use polymers which have steel fibers in it. So there can be various ways to go about in making composites. So now what I will do is I'll actually derive something where I say that how do we know the properties in composites, and I will talk about only one-dimensional composite where there is a fiber and matrix in one dimension. So there is something called rule of mixtures to find composite properties. And this rule of mixtures, if you'd like to say, is what I can say is I will take 2 cases. The first case will only have so I'm imagining that I have a composite in which fibers are laid like this. Fibers are laid like this. So fibers are in one direction and remaining. So this portion is matrix, and these are 3 fibers, if you'd like to say. So now I can find out what will be the effective property, because I know the property of fiber. fiber, and another property of matrix. Now I want to find an effective property of this composite. So there are two limiting conditions. The first limiting condition is if I load in the direction of fiber. In what direction will it be the best? It will be best and strongest and stiffest, right? It will be strongest and stiffest in the direction if I load in the direction of the fiber, right? So that will be one condition. The other condition, it will be weakest in which condition? If I load it like this. So if I load it parallel to the fiber, that is the best case condition. If I load it perpendicular to the fiber, if I load it like this, this is the worst case condition, right? So we will evaluate for both these conditions. I said we'll evaluate how we can get the properties of the composite from its constituent. Okay, let's do this, right? So if I have this and I'm pulling it like this, F and F. What is here is if I pull it, the strain or the deformation, the strain and deformation, because length is same, initial length is same and I'm deforming. So the strain which will be induced if I pull it, it will change a little bit. It will increase in this direction. Sorry. So it will become something like this. It will become something like this. So the strain and deformation in both the fiber and the matrix is same. So let me say, so epsilon F, if I'm using F subscript for fiber is F and matrix is M. So epsilon F is equal to epsilon M is equal to the composite also. Epsilon C is the combined property of the composite, right? So now I say epsilon F, epsilon M and is equal to epsilon C, right? And what I say is, so strain is same, but load is shared, right? So basically I say sigma F shares the maximum load, right? Sigma F, and then there is sigma M, what is just in the matrix, and then I have sigma C, which is the combined thing. So basically what, if you want to see this, it will be sigma F times AF, which is the area of this total cross-sectional area of the fiber will be the force, right? Sigma F AF plus sigma M plus sigma M AM, area of the matrix, should be equal to total force. Total force is shared by the fiber and the matrix. Of course, fiber will share more of it. And this F, I can say that this will be sigma composite times total area. Total area of the total area, which is total area would be, so this is a effective stress. This is some sigma effective stress, which is I'm taking averaged over this area, AF plus AM, right? Now what will happen is I say sigma F. So sigma F is nothing but E times epsilon F. E and E are separate. Modulus velocity of fiber is separate than fiber of modulus velocity of matrix. So EF times AF, EF times epsilon F is sigma F times AF plus EM times epsilon M times AM is equal to E composite epsilon composite divided by AF plus AM. Right. Let me transfer this to the next page. Force balance I'm doing. So by doing force balance, what I see is I get, I'll just write it again. EF good. EF epsilon F times AF divided by AF plus AM plus EM epsilon M AM divided by AF plus AM is equal to EC epsilon C. Now AF plus AM, if you see, AF plus AM is the cross-sectional area of fiber plus matrix, which is total cross-sectional area. And if you imagine, I'm talking about area, the length is same for everything, right? The length is same. The length is same. So basically, AF divided by AF plus AM is nothing but volume of fiber divided by total volume, which is the volume fraction of fiber. Volume fraction of fiber F, and AM by AF plus AM is nothing but volume fraction VM by VT, which is 1 minus F, because there are only two constituents. If one is F, the other is 1 minus F. So let me write it, and I also know that epsilon F is equal to epsilon M because they are undergoing the same strain, epsilon C. So with this, I can rewrite it EF times F plus EM times 1 minus F is equal to EC. This is the upper bound. This is the upper bound of volume of mixture, rule of mixture. This is called rule of mixture. This is upper bound, rule of mixtures, upper bound of rule of mixture. Now, if I were to find out what will be the lower bound of rule of mixtures, I can do that as well. Okay, let me go back. So the other one, what I was trying to do is I say that it will be something like this. My fibers will be oriented like this, like this. So these are my fibers. These are my fibers. This is my fiber. This is my fiber. This is my matrix. This is my matrix. And my loading is like this. What will happen in this case? In this case, my sigma F will be equal to sigma M because stress is same. The strains are not same. Sigma F is equal to sigma M is equal to sigma composite. All stresses are same because you are giving the same stress to the entire material. But what is happening is the deformation in fiber plus deformation in matrix will be equal to deformation in the entire composite. So there are two things, 1 and 2 conditions which will be there. Now let's go ahead and derive this. So delta F So now if I have delta F plus delta M is equal to delta C, let me do this. And then I also know that EC times epsilon C will be equal to EM because sigma M is E epsilon, EM epsilon M. Let me just write it properly. E times epsilon M is equal to EC epsilon C. FF. EF epsilon F EM is equal to EC epsilon C. This comes from this equation right here. Now what I can do is I can basically say that I know that delta M plus delta F plus delta M is equal to delta C. So what I can do is I can basically equate from here that EM epsilon F, if I want to find out what will be epsilon F will be equal to EC times epsilon C divided by EF. Right? And if I were to find this out, so this is one equation, and I can do the same thing for epsilon M also. I can find out epsilon M will also be equal to this thing, EC times epsilon C divided by EM. So I have these two things. Now I know, so let me go ahead and do this, rewrite this again. So basically I had epsilon F, add epsilon is F is equal to epsilon F is equal to, let me just go back, epsilon F is equal to EC epsilon C by EF is equal to EC epsilon C by EF, and epsilon M is equal to EC times epsilon C by EM. Now, if I want to say epsilon will be nothing but delta F by length of fiber is equal to EC epsilon C divided by EF. So delta F is equal to EC epsilon C LF divided by EF. Delta M is equal to EC epsilon C EM LM. Right? And I know delta F plus delta M because the deformation in fiber and deformation in matrix should sum up to be the deformation of the composite. Equal to delta C. Just give me a minute. And then I'll formulate this is equal to delta C. So basically I say EC. Okay. So I should get EC times epsilon C times LF times EF plus EC times epsilon C times LM divided by EM is equal to delta C. Delta C is nothing but delta C. If you want to find out, delta C should be equal to delta C. If you want to find out, delta C divided by LC. LC is nothing but LF plus LM. Delta C divided by LF plus LM is equal to, this is the strain, and this is the strain. So we just put the strain here. So this would be the plus LM is strain is equal to EC times EC is equal to sigma F. Right. Wait, let me just do this. So the deformations you sum. So deformations you sum. This is delta. This is delta composite, and delta composite is EC epsilon C. This is epsilon C times, so delta C. Let me just plug this here, sorry. This is delta composite. So delta C divided by LC plus LF plus LM plus LF. So this is total length, LF plus LM. So LF plus LM will be equal to, will be total length. Look at LC. So delta C by LC will be epsilon C. So now what I can do is I can put epsilon C times LF by LM. Here, epsilon C times LF plus LM. Right. Now what I will get, epsilon C will all get cancelled. So what I get here is, what I get is 1 over EC. 1 over EC is equal to 1 over EF LF by LF plus LM. LF plus LM plus 1 over EM LM by LF plus LM. Okay. And now let me just simplify this. Okay, just 1 second. So this is nothing but LF by LF plus LM is nothing but, this is 1 over. So this is LF by LM is F times 1 over EF. This is F, because now length is the volume fraction. So this is nothing but F. This is F, and this is 1 minus F. This is 1 minus F. 1 minus F. So this will become like 1 over EC is equal to F by EF plus 1 minus F by EM. So these are the two absolute limits. One is the inverse, the other is the rule of, so this is the inverse rule of mixture, sorry, inverse rule of mixture. Inverse rule of mixture. Okay, these are the things. So these are the two brackets in which composite actually works. Now what happens is, composites are used mainly in the new planes. So this one is actually a very important aspect in composite. Airbus 380 has a lot of composite. This is composite, this is composite. The fuselage is still not composite. But Dreamliner 787 has 50% composite. Even the fuselage, this portion is also composite in Dreamliner. And lot of expensive cars, Lamborghini is made of composite. So what I will do is just wait here and give you a good video of this. Give you a good, show you a decent video of it. The 787. Can you guys hear the video?
No, sir, we can't hear.
So can you just share the link of the video?
Okay. So now let's stop sharing. So now what we do is we'll just open the session for questions. And if you have any questions, just ask me now. So I think lecture portion is over today. So if you have any questions, just ask me. Okay. So now it's open for all. You can either post the questions, Chaitanya can read it out, or you can unmute yourself and ask any questions you want on lectures today. No questions?
Sir, if the loading is at an angle, you have shown it if it is perpendicular or parallel. So if it is at an angle, then what do we do?
It will be between these two.
So there's no weighted average of these or something.
No. So what you are trying to do is you can actually solve it if you want, right? You can have a perfect solution for it.
Okay.
But I'm bounding it. I'm just giving you two extreme conditions. So either your stiffness will be like this. So there are two conditions which I showed you. Either it is like this, volume fraction times E of fiber, and 1 minus F volume fraction times E of module is equal to E of composite. That's one. This is the highest E you can get. This is just the best stiffness you can get out of the composite. And the worst you will get is this, the inverse law. 1 over EC is equal to F by EF, 1 minus F by EM. So these are the two bracketing results. So I'm just giving you rule of mixtures, right? If you have two different distinct composite elements of composite, how do you get a how do you get an estimate for the properties of the composite? Because the composite will behave differently than the constituents, right? The entire composite will be stronger than the matrix, but weaker than the fiber. And this is the relationship. Two extreme cases. One in so because if I load in the direction of fiber, I get the best property. If I load then the entire load is taken by matrix in some sense, right? Fiber is not taking that much load. If I'm doing that in the perpendicular fashion. So these are the two extreme conditions.
Okay, sir.
Anything else?
So in the two equations that we found in the two cases, if we want to maximize EC, and if assuming that EF is greater than EM, then F will have to be 1.
EF will always be greater than EM.
That does not make sense, right? Because
EF is much greater than EM. So fiber is much greater than EM, sometimes many times greater.
Yeah, so in that case, if EF is greater than EM, which is always true, then F will have to be 1 to maximize EC.
हाँ तो खाली फाइबर यूज कर लो ना भाई, right? So but खाली फाइबर तुम यूज कर नहीं सकते ना, because fiber is brittle. So the polymer matrix is giving you some ductility, right? You cannot use glass fiber, right? Can you make a glass chair or glass table? But glass fiber table and chair you can make, you can bend it, you can form it. You can injection mold it. Glass पे injection mold कर पाओगे क्या? और कोई बेंडिंग स्ट्रेंथ नहीं रहेगा, ग्लास में बैठोगे पट से टूट जाएगा. बट ग्लास फाइबर डाल के पॉलीमर बनाओगे, you will get amazing properties. You can do pretty much whatever. You can make pipes, you can make chairs, tables, super strong table chairs, right? So that's what I wanted to give you, that you need certain stiffness, right? What you are doing is तुम 10% 20% ग्लास डाल दोगे ना उसमें पॉलीमर में, your properties will be superior, much high. You will get a pretty good composite E, much higher than what you get for from just pure polymer. Okay. Any other questions you guys have?
Sir, in the case when both there are horizontal and vertical fibers, and like the stitched case you mentioned.
Let me just pull that thing. Yeah. Which one are you talking about? 1 or 2?
So the planar reinforcing phase, I think you mentioned.
Oh, you're talking about woven
Yes,
fabric,
yes.
right? Yeah.
So in
What?
that, will that be a superposition of both of these systems? Like,
Oh, woven fiber are a different beast by itself, because woven fiber, it will have a different E1 and E2 in different directions. So it like, instead of having just one dimensional composite, woven fiber have a bidirectional property. They have E1 and E2. In X direction, they will have different stiffness, Y direction they will have different stiffness, because they're woven. You get
okay.
me? So they will give you, they will give you properties in both the directions, good properties in both the directions. If you do uniaxial, right, you are getting properties only in this. So you'll have a compromised property in both directions, but much higher than what you get. So if you see in the second case here, right, you're not getting any reinforcement. But if you weave it, you're right, you'll get much better property than this. You're right that you'll get a bidirectional strength in that case.
Okay, right.
Any other questions you guys have? So I will post the. I don't know why you were not able to listen to the voice of that Boeing video. I'll post it just after the class so that you can look at it at your leisure. It's a nice video in which the parts come from all parts of the world, and they assemble it. They're all made of composites, very light plane. So if you sit in, for those who have not sat in Boeing 787, Air India has 25 of those. Those are very comfortable, because in the older planes, you could not have enough moisture. So you will get dehydrated if you go for long flights. If you take Boeing 777s, you'll get dehydrated, because they will keep at very high, the dryness level is very high in the plane. But 787 is very comfortable because they can keep a lot more moisture, because it's not a metallic plane. So the corrosion is better. Corrosion performance is much better in the composite plane. Any other questions you guys have? I'll be happy to answer it. If not, I just wanted to give you some flavor of composite, because you have studied metals, you have studied plastics, some form, but this is one class of elements which you had never studied. So I just wanted to dwell upon it. And in the next class, what we will do is I'll just give you some brief overview. What we want to do is in the next class, what we will do is we'll do this. We'll do different properties, and we'll try to basically understand. Let me share this, and this is where I'll stop. Yeah. So we'll do something like this. We'll try to figure out how the mechanical properties affect the performance, and how do we choose different material. So if it is stiff, it is not stiff, it's not strong, not tough, too heavy loads, too heavy things. So you need, so if it is heavy, then what? So these are the illustrations. These are some of the mechanical properties which you need to, which creates problems. So how do we select a material so that these problems do not arise? So that's what will be the entire focus of this. On Thursday, we'll discuss more. Okay. And for those who want to attend the other lecture, we'll figure something out. I will still teach the class, but you guys can look at the video, and I can have a session if needed to take care of it. Okay. So let me just stop sharing, and we'll call the class. The class is over. Okay. Thank you so much for attending.
Sir, the Autodesk sessions, they are going to be for like multiple weeks, around 8 or 9 weeks.
Yeah,
12 weeks. So will that be okay? Like, that was the doubt of a lot of people, that will that be okay? Like, will you be conducting classes again and again for?
No, I'll not conduct classes again. I will upload the video, and if you guys want, I can, in the evening 20 minutes, I can have discussion session. I'm not going to conduct the classes again.
Okay. Yeah.
I'll just have, so you watch the video, we'll upload the video, Chaitanya will upload the video, and then we will have a face-to-face discussion for 20 minutes.
Okay.
Because I cannot just do that, right? I cannot just keep on repeating the classes. It will be too much for me.
Yeah.
Either ways, only half the people show up for the class. So it doesn't really matter, right? Might as well learn this or that. Doesn't really, if you feel that it is useful, go ahead and sit in that class. I have no issues with that one. Okay. But my argument is I don't feel that a software learning should take 12 weeks, in my honest opinion. Okay. I think it is too long a time for learning a software. That's my opinion, but now it's your call how you want to do it. Okay. Any other questions you guys have? I think we are almost getting close to the class. If you have any questions, concerns, comments, I'll be happy to address it. If not, have a very good day and we'll meet on Thursday.
Monday.
Oh, today's Thursday, is it? Okay, we'll meet Monday. Sorry about that. Yeah. Okay. So have a good day and we'll meet again. Bye bye. So I'll close the session in that case.